Thank you for the very kind introduction and build-up. So hopefully I do something along the lines of what I've been purported to do. Some of you may notice that I'm not Andrei Kuipers, much as I'd like to be. Some ways I wouldn't want to be, because I didn't really want to be an astronaut. People thought if I had applied to the astronaut corps, I would have ended up like Homer in space. If you've ever seen that episode of The Simpsons when he breaks the ant farm on EISS, that would have been me in real life if I'd ever gone there. Anyway, I digress. Andrei, unfortunately, is not well this week and was unable to attend. He sends his regards. In his stead, you've got me, unfortunately, and I'm going to give you my version of the Rosetta mission in the next couple of minutes. So everything I know about Rosetta. Bear with me, I have been shuffling with my slides and my laptop's over there, not here. So I have to remember what I shuffled. I give this on behalf of all the Rosetta teams. Some of them have actually come in here today, so some of them might be here, some members of the team. I put this here. This was my selfie, the Oscars selfie. It also reminds me that I should take a selfie of you lot, so if you bear with me. Right, smile, look like you're enjoying yourself. There you go, you won't be able to see that it's you. Okay. I like this selfie because it shows all of the key people. This is during one of the science working team meetings in ESAC, actually, near Madrid, one of the ESA stations there. You can see a number of all of the Rosetta team. We've got members of the science ground segment, some of the key PIs. There's the boss, Patrick Matin. This is coming out. And if you all look to the back left of the theatre, there he's standing there to make sure that I say nice things about, or sitting there to make, he's waving now to put the pressure on. Okay, and there are other members of, I just saw Mark outside. He wasn't sure whether he was coming to see me talk. He's the Miro PI. We also have Santa Claus in the back there. This is Fabrizio, who is the PI of Vertis, and then Holger. And also we've got Sylvain Lodio, who is basically the bus driver of Rosetta. He's the satellite operations manager. He's the one that makes sure we're in the right place or where we think we are. Anyway, there's a number of faces that you may see around EGU this week.
You promise to speak a little bit slower.
I'll try. Okay. It's not going to help me drinking lots of Coca-Cola and coffee. This was actually last year. We had a press conference announcing this fantastic result that we had combining the Rosetta orbiter and the Philae lander magnetic field measurements. Also with the BBC journalist joining in, Jonathan Amos. But a lot's happened since then. I try and touch on some of it, but it's still ongoing. Hopefully you'll get that from my presentation, which I will try and slow down. Why do we look at comets? This is an image or a graphic of the solar system some 4.5 odd billion years ago, where we had a cloud of dust and gas which collapsed and formed a sun, and then the remaining material started to smash into each other and form the planets and the moons. Of the material that was left over, this debris, we consider that that material, the small bodies of the solar system that we know today, kind of things like asteroids and comets. And so those small bodies are kind of the leftover debris, the leftover ingredients that went in to form the solar system itself. So that's why it's important to look at these bodies, to kind of get an idea of what was there right at the beginning. Just as a reference, this is Tauri TL, I think. I can't remember, I'm not an astronomer. But it's actually an image. If you saw that disk with the disks carved out of it, this is actually a real image of a young solar system way out there in space. So they do exist, not more than computer graphics. And we look at these small bodies, as I say, because we think they're ingredients from the solar system, origins, and to kind of get an idea or look at the questions, the big questions like, why is there life on Earth? Why did we get here? Why is the Earth like it is? We look back in the early stages of the solar system where we had something called the late heavy bombardment, where there were lots of things colliding into the Earth and the inner solar system. Around that time, we believe, at least some theories say, that the Earth didn't have any water on it anymore, so something must have brought the water back, redelivered it. And we look at the asteroids and the comets as a mechanism to do that. And also, perhaps, given that they also contain lots of other funky stuff, which I hopefully will get to, the building blocks of life. So maybe that was what delivered the initiation or the ingredients, again, of material that could go on to form all of us in the room. We've been fascinated with comets for many, many years. This is a cartoon depiction of actually a cave drawing that exists in Portugal. And one can only imagine I think it's something like 5,000 or so years ago, what our ancestors were thinking when they saw this burning feature in the sky, this comet in the sky. I would imagine, and we have seen with other more recent historical documents, that they found this to be quite worrying, that it was a portent of doom, that something bad was going to happen. But as science usually does, it helps you to understand things, and so we have a much better understanding nowadays of what comets are. Still not enough, that's why we sent Rosetta. But nonetheless, we understand that we have this very small nucleus. It's only a few tens of kilometers in size. And that creates this massive outer atmosphere, the coma of the comet, which is then drawn away from the sun direction into a massive tail that can be millions of kilometers in size. And so in certain circumstances, for certain comets, we can actually see them from the ground, that they're so bright. These tails are full of dust. That dust reflects sunlight, and you can see that from the ground. And the activity that we're interested in comets, certainly with Rosetta, is driven by the sun. This is an orbit of actually the comet we're at with Rosetta in black. When it's far away from the sun, it's very inert, it's still frozen, but when it gets closer to the sun, it becomes much more active. The ices sublimate, they change into gases and flow off of the comet, and we get this wonderful tail and the typical comet that we know and love, or the typical comets that we know and love. And of these small bodies, we consider, or some of us do, that comets are more interesting because in this evolution of the solar system, we find that the comets have resided very, very far away from the sun, so the material that was there at the beginning, the volatile material, was locked in them like ice, as ice. And so when they come back in again, they're redelivering and bringing back these signatures. They're like a time portal or a window into the past. So we really get an idea of the material that was there right at the beginning, possibly predating the formation of the solar system. Spoiler. We started in Europe with Giotto way back in the 80s. This is our first foray into deep space. We went to the comet Halley and we uncovered some fantastic things. We found the fact that there was this nucleus, a solid nucleus, and that it reacted readily with sunlight. That was what was driving the activity. As you've already seen, in '86, this is what I looked like. For reference, I put that up to demonstrate, and this is something that Olivia Vittas was talking about in a presentation about JUICE, how long, and I think those of you that have seen the Cassini talks as well, how long it takes to get a mission going. So at the same time that Halley was flying past Giotto, people were already talking about Rosetta. Actually, at the time, it was, you won't see this, it says Rosetta Comet Nucleus Sample Return. This was from 1987. This is a report, a joint ESA-NASA report, investigating or talking about going to a comet, grabbing a piece and bringing it back. That was the dream 30 years ago. It was shown that that dream was a little bit too extravagant. Some would say, actually, maybe some of you asked that question earlier this week, it's still probably too extravagant to do. Oh, hello, Annette. Sorry, I've just seen you. Sorry, my mind was taken. It's somebody I know from Mestec a couple of years ago. I digress. Where was I? Yes, Rosetta was formed 30-odd years ago. It was conceived then, and most likely we still haven't got the capability to do that. And as a result, then we decided not to do this comet sample return, that we did something else. We sent a lander instead. We've had other missions since Halley. I also include all of the spacecraft that went to Halley. There is a flotilla or an armada of spacecraft from different agencies. I list just the comets that have been imaged because we have observed comets in other ways, mainly from plasma, but I just talk about the ones that have been observed or had photographs taken. All of these provide us with a snapshot of their target body. They whizzed past at hundreds of meters or hundreds of kilometers distance and also very high velocities, tens of kilometers a second. So they really just had a snapshot and then they went. So we knew that we needed something like Rosetta that would go to a comet and sit next to it as it went past the sun, as it went through its closest approach to the sun, to observe how the comet worked, how that activity was being generated. The Rosetta mission got its name from these two objects. We have the Rosetta Stone on the left, which has 3 texts on it. It was key in deciphering the ancient language of Egypt. So with this stone and also the Philae obelisk that was found in this temple, they were used to decipher the ancient language of Egypt, and we make that comparison with Rosetta, the Rosetta mission, being key in deciphering the ancient language of the solar system. There's a colonial discussion to have here, that the fact that there was a lot of discussion about whether the French did it first or the English did it first, and that you may know that neither of these articles reside in their original location, but they are in that's in the British Museum, and this is found actually in a country garden in Dorset. But that's a whole other presentation. This is a graphic of the spacecraft. It's 32 meters from wingtip to wingtip. It weighed around about 3 tons at launch. Over half of that was fuel to get where it had to go. The Philae lander was about 100 kilos. To give you an idea, those of you that play basketball, 32 meters is roughly the distance between the nets. So that's how big this spacecraft is. It's quite a large spacecraft. Those of you that play cricket would know that that's roughly 1.5 times the length of a cricket pitch, or a chain is the measurement of a cricket pitch. So you've actually learned something in this talk. The object we went to, 67P, Churyumov-Gerasimenko, I will do a better job at pronouncing that in a moment, is the target object. It has an orbit of around 6 years period, was discovered by Klim Churyumov and Svetlana Gerasimenko. This is the original photographic plate on the bottom left here from which it was discovered. This is what we thought it looked like up to quite late in spring 2014. This was based on light curve analysis from Hubble and other images. And 67P, because it's the 67th periodic comet, Halley was designated the first one. And here's a demonstration of how you're supposed to say the name. Oh, come on.
Churyumov-Gerasimenko.
And for want of time, I'll just call it 67P from now on. Also, we had a presentation on JUICE earlier on that was demonstrating the fact that you need to do a lot of things from a flight dynamics perspective to get to these outer planets, to get to these outer reaches of the solar system. Because although we had 3 tons and over 1,500 kilograms of fuel on Rosetta, we still had to borrow energy from the inner planets to catapult us out to the orbit where the comet was, to chase it down. And this took us over 10 years. And in that time, we did some flybys of the Earth. We did 3 flybys of the Earth, 1 of Mars. In fact, in one of the flybys, you can just see this line here. That's actually an image from the ground of Rosetta as it flew past Earth. We went past asteroid Stein and asteroid Lutetia. Let me go back and just show those again. Lutetia was a much bigger asteroid, about 100 kilometers across. Steins was about 10 or 15 across. You see it's quite blurry here. This is, as I discovered when I came onto Rosetta, one of the first conspiracy theories associated with Rosetta, that the whole mission was designed to go to this asteroid because it's not an asteroid, it's a spacecraft. It's not. So the conspiracy goes that because the images are blurred, it's because the ESA are holding back the images to protect the aliens on board this spacecraft. It's not. There was just an issue with the camera at that time, which was certainly fixed by the time we flew past Lutetia a couple of years later. And we did a selfie at Mars. So this was taken by the Shiva camera on board Philae, looking down the solar panel of Rosetta. And here you can see this rather popular planet, unfortunately. People send things there and take up data volume that could be valuably used for a Rosetta mission. So please, everyone on Mars, turn off all your instruments and let us have all of your data volume. Thank you very much. Talking of Mars missions, here I use the vernacular or the terminology used by the Curiosity rover, where they point arrows at their science targets. So now you know that this is Mars. So we went far away from the sun, far enough such that there wasn't enough power to power the spacecraft, and we had to put it into hibernation. So that was done in June 2011. And at that time, I was working on the wonderful, brilliant cluster mission, which is still going. It's a mission, a 4-spacecraft mission investigating the three-dimensional aspects of the plasma interaction that works, basically the outer atmosphere of the sun and how it impinges on the Earth's magnetic field and drives things like the aurora. So I was working on that, and then I moved to Rosetta for my sins. The first thing I did was make sure everyone that worked on Rosetta had tattoos. That was my first job. The reason I show this is part of the massive team that works down in Spain. There's also a team that works in Darmstadt on the mission operations, but these are some of the key people that work closely with me as project scientist in trying to get all of the wants and wishes of the principal investigators, the lead scientists on the mission, to get all of their instrument commands on in a way that satisfies or equally doesn't satisfy everyone on the mission. I'll leave it at that. But they're key in this mission, as are the hundreds of people that work on this. It's key to know that it's not me at all. I'm a small cog in this, and there are many, many more important people than I that work on this mission. And then we came out of hibernation in 14, or we were trying to at least, before January 14. We started doing different things in ESA. We started driving more communications and outreach activities. We had the Wake Up Rosetta activity, where we were encouraging people to suggest how they would wake up a spacecraft. And we run some competitions. We had a winner, a guy from Poland, and also a whole school from Greece. And we also got the Rosetta team to do a similar video on how they would wake up Rosetta. And we were waiting, well, actually, oh yeah, here's another one. Sorry, I forgot about this one. Does everyone know the Big Bang Theory? Good. Some of you will understand this then. This is Joel Parker, who works on the ALICE instrument on Rosetta. He's also deeply involved in the New Horizons mission. This was a joke video that we put together.
So if we want to wake up Rosetta, what's the best place to do it? How about the Rosetta Mission Control Room? Well, here we are. Let's give it a try. Door's locked. Now, what would Sheldon Cooper do in this situation? Rosetta! Rosetta! Rosetta!
Now, that's not put on until that happened. As is usual when you have engineering and science interfaces, the interface at ESOC is a locked door. And so we really were knocking on the door, and they opened the door at main control room to say, what the bloody hell are you two doing? I think it worked well. Ultimately, no, it's still not ultimately. I've got another sojourn. Okay, when I moved from cluster to Rosetta, I told my mum. My mum was constantly asking me what plasma physics was and what cluster was doing for the years that I had worked on cluster. It was always a thing that I had to remind her every so often what space plasmas were and what cluster was doing. But when I told her I was moving to Rosetta, that it was going to a comet, she immediately understood everything for some reason, which was a great disappointment to me as a plasma physicist. But nonetheless, she said, oh, comets, yeah, I know comets. Rosetta, oh, she said, Rosetta, I know a song called Rosetta. And she pointed me to this song by Alan Price and Georgie Fame called Rosetta, and I hopefully have turned the volume down enough because I will play it to you because it's poignant for the time period where we were waiting for the spacecraft to come out of hibernation.
Rosetta, are you better? Are you well, well, well? Rosetta, are you better? Are you well, well, well?
The song loses credibility in terms of comparison to the Rosetta mission shortly after that because it's actually a song about a young lady who has drunk too much whiskey. Although the fact that we have found alcohols on the comet, there may be some relation there, but certainly. And we were waiting for this in January 2014, the carrier signal, and we were all very happy when it came back. And then we started the tweets from ESA Rosetta with gusto. We had the Hello World tweet, and actually there's Emily Baldwin tweeting that at that time. So she's the main, blame her for the tweets from Rosetta, put it that way. So we very quickly at that time period had to go from this grey potato image that we'd got previously to finding out that actually the comet was this funny shape, whether you call it a duck or a boot. I think this is an accurate depiction of our faces when we saw it as well. But we thought, okay, we know we've got a couple of months to find somewhere to land on this thing. And this is a good thing to put in your head, that with Mars missions, with Moon missions, we have taken a long time and spent many missions to try and decide where to land. And we sent 2 spacecraft to an object, we didn't know what it looked like, and we had to land on it by when we got there within a few months. So that time scale and that schedule was rather compressed. Anyway, we thought it's a funny shape, but hopefully it'll be smooth. And it wasn't very smooth at all, as we found out. For reference, I show a ground-based image at the same time. I think at this point, the outer atmosphere, the coma of the object was something like 18,000 kilometers already in extent. Another conspiracy theory, seeing as I found these on the internet, I find them quite amusing. Apparently, this thing here, which is actually a vent that we are very interested in terms of outgassing, is we photoshopped it, and it was actually a dome structure. There's a house there. And on the head lobe, there's something that I can only describe as looking like a farm in Iowa, where you can see car tracks. It's not, it's a comet. But then I am the man, technically, because I come from ESA. So anyway, reference, we got a good feeding. The estimates that we had of the grey potato in terms of scale size were quite good. We were pretty good with that. We have really reference material in terms of where you are. So, you know, for particular audiences, I haven't got one for Vienna, but I've got a couple of towns. So there's London as well for reference, Rome, Madrid, Paris. I gave a talk at a Star Trek convention in Germany last year, and I'll give one again this year. It's very fun. And so I had to think, well, what do you use to put across the size of the comet for this kind of audience? And luckily, there's a physics teacher from the US who has done this for me for this audience. This is a tough audience. You've got Klingons there. Yeah, so Christopher Beck did this. He's got these, so you can put it in context with some of the science fiction objects that you're familiar with. Again, the conspiracy theorists have probably noticed that the Borg cube has a great similarity to the surface of... also, we got Battlestar Galactica. That will come up a bit later on, hopefully, if I get there. And I'm a Star Wars fan, so you put it in context with the Death Star 2, and, you know, it goes to show how big the Death Star 2 is. And I was surprised how big a Super Star Destroyer was. It's about 19 kilometers in length, apparently. It's a lot of stormtroopers. I digress again. Okay, so this time period, in 14, we were carrying out some of the most extravagant operations that we've ever carried out in ESA to try and get a feel for what the comet was like, the near-comet environment, what the gravity was like, what the atmosphere was like. So we stepped closer and closer to the comet to decide where we were going to land and also get a feel of how to navigate around this object. During this time period, in August, September, we were trying to decide where to land. We had 10 land candidates, then it was 5. Then we went down to 1. This was done from an engineering but also a science perspective. We had the science teams here discussing and prioritizing which landing site to go for, and ultimately we went for Agilkia on the head lobe, or Site J. Another selfie. What I didn't note for the Mars selfie, that there is no duck face there. Those of you familiar with selfies will know what a duck face is. There wasn't one before. Technically, if you consider the Rosetta comet or Churyumov-Gerasimenko as a duck, then there is a duck face in this selfie. I used to get the comet round the wrong way, so it was another part of the comet that was showing, but I won't go into that. The evening before the landing, there were some issues with the gas thruster on the lander. There are 3 mechanisms to land: a harpoon, a gas thruster, and also screws on the feet of the lander. At this point, we found out that the gas thruster wasn't going to work, and we had to go through a set of procedures to allow us to go forward with the mission. And by 3 o'clock in the morning, that was a go, and that was why we did what we've done. But it was a worrying time nonetheless. And again, you saw all the key figures during that period. So we released, this is an image from Shiva looking at the spacecraft from afar. It's blurred because Philae was rotating. Then we have these set of images taken from the orbiter of Philae. Nice pictures because you see that the legs have deployed. I like this because it reminds me of a cat. And you know that when you throw a cat, it always lands feet down. So I like that image. And I scientifically know this because I used to try and make my cat, when I was young, land on its back. And it never did. It ran away for some reason. But it was a good analogy for me to remember poor Jim. This is a room near the main control room. Well, actually, you've got Holger, the PI of the camera. Emily again. She has a USB in her hand. We're all happy because I think this was the transfer of data. So this was the set of images that we just got there being handed over so we could put them out. So things were moving forward. We have the images from the ROLIS camera on board the bottom of the lander as we approach the surface. And so that loud noise was actually the seismic sensors on the feet of the lander, giving us an indication of what the surface mechanics were like. From these measurements, we got a feel for roughly how much dust was on the surface, a few tens of centimeters, the tensile strength of the surface, that it was like kind of loosely compacted snow, a bit like lunar regolith, around that kind of feel, as it were. So we're all very happy. And we got within 120 meters, I think, of where we targeted. We released from 23 kilometers, so that's not bad shooting. We tried to fire the harpoons, and they didn't work. And so we had a little jaunt across the surface of the comet. This is the first panoramic image, which was supposed to have been from the surface, but wasn't, and is blurred for various reasons, because we were in motion. So this is the approach, and then the impact you can see before and after, and then we scooched over here to the right. Which meant for the lander teams that they had to rapidly change what they thought they were going to do on as instrument operations. And this is what was changed here. It's basically a Gantt chart showing all the different operations and what was moved around. I'll have to speed up a little bit, but I'll try and be slow as well. This is an image, well, basically a photograph of the whiteboard in that room where Holger and everyone was, and we were trying to work out from the panoramic images from the lander when it had finally come to rest where it was pointing. And these are the images we were trying to work that out from. And ultimately we've got this better idea now of locally where it is, that we had this bouncing trajectory. We roughly know where it is within a few 30 meters or so square, roughly. This set of bounces was actually good in a way. That actually enabled the result that I mentioned earlier on, this magnetic field result that we had, we showcased last year at EGU. Without that, we wouldn't have had the expanse of measurements across the surface of the comet, so it was a good thing. A number of people were very, very happy here. I'm not sure if Stefan's still in the room. He was here earlier on. He's a project manager of the lander. Vicente Companies is the head of flight dynamics. He's the one that designed the trajectory to deliver the lander, so that's why they're happy. Catherine Altweg, my dearest enemy, apparently. She's one of the PIs of the PI of the Rosina instrument. And then some of the flight control team, Armel, who was the kind of liaison with ESA with the Philae lander. And I put a show up here, there's Holger again, but Claudia Alexander, she was the project scientist on the NASA side. She was the equivalent of me on the side from NASA. She was there at the landing, but unfortunately she passed away last year. So this is a big loss for the team, and I always have to put this up there because at least we knew that she got to see the landing, but she hasn't been able to see all of the other great stuff that's come out of Rosetta since. But still, she was there, and it is a big loss for us. And then ultimately, after 60-odd hours of work, the lander went to sleep. And I went home, and life went on as usual. And science was starting. So this is June 14, June 15, and more recently in Leiden in March 16, the science team's meeting to discuss science of this object. This is a nice graphic actually put together by not a scientist, but a guy that's very good at 3D rendering, Matthias Malmer, using all of the publicly available images. It's a really nice job by him. So, one of the things we are wondering is what made this object the shape that it is. And we will look at the various layers and the regions of the comet, the surface features, to get an idea of that. We focus on certain areas where we see lots of layering. You see these layers, they're plateaus everywhere. And these are all over the comet. And we have a look at what their orientation is with respect to the comet's surface. And we find that actually, if you think of an onion with various layers, you can consider that it's more like two onions stuck together when you look at the orientation of these layers than one single onion. You can try it when you go home, bite out an onion and try and make it look like the comet, or stick two onions together. I'm sure most of you will just stick two onions together. But that's basically what the physics and the science behind this was, to look at the orientation of the different layers, and then look and consider that this is most likely a result, this duck shape is a result of the collision, the low velocity collision of two smaller comets. So we look at the morphology, the different features on the surface, and they've been named after Egyptian gods to kind of keep the theme. There are female deities on the head of the duck and male deities on the lower body of the duck, if I remember. And you see, not all of the regions of the comet are featured here because this was earlier in the mission, in 15. This is driven by the fact the comet has seasons like we do on Earth. If you see on the top left, this is in October, we're really looking at the northern part of the comet. That's where the sun is illuminating. And as we go around through perihelion and back round again, because of the tilt of the orbit and the tilt of the comet's rotation axis, it shows different parts of itself to the sun. And that's what we see here. So we go in May through equinox. You can see on this model that not much is actually filled in. That's because we didn't know much about the south. Then through summer and late 2015, we were really seeing the southern hemisphere, and so when we went through equinox again, you can see that we've been able to fill in the southern hemisphere of the comet, and we get a more three-dimensional or full coverage of the comet. But that's why we have different regions being illuminated, or the reason we have different maps is because different parts of the comet are illuminated at different times. We're now able to fill in, so this is a weird projection of the comet. That's the bottom of the comet, the base sort of this part of the duck, and then this is the top of the head here, but projected out. So we have all of the regions named. We have various regions, they're named after their physical appearance. We have very dusty layers that you can see here, dusty regions. This is somewhat similar to the Mat region, where the lander was first hit. And you can see the difference here before and after. You see these indentations. From those indentations, the scale size and the knowledge we have of the rough density of the comet, which is about 500 kilograms per meter cubed, that about 180 kilograms of material were thrown up into the air, as it were, or thrown off the surface. And some of that was actually captured by the Philae detectors as well. We have consolidated regions, which are more compact. Maybe you would think rock-like, but of course it's not rock-like, but they're consolidated regions. And we see lots of fracturing all over the comet, down to meter scale. It looks like lizard skin. And this paper by Rami kind of points at the fact that this is driven by thermal stresses of the comet, that we have this massive transition in temperature. The comet rotates every 12 hours, but the sunlit portions of it only receive sunlight for something like 4 hours in some places. And so you have this massive fluctuation over 200 degrees in that time period. So you can imagine the thermal stress that you are putting on this object. And that's what we think drives these particular features. And we've also seen this down with the Shiva camera at a very small scale, similar fracture-like creatures. So it's fracture-like features, not creatures, features. So it's ubiquitous, it appears. And we have this nice crack in the neck as well, which we think is actually driven by thermal stresses. The neck is very interesting in that it has lots of this dust laying around in the neck region, the happy region, named after the Nile Valley. And we see dune-like structures and wakes around boulders, a bit like you see on the beach, but that wouldn't happen here because we haven't got horizontal winds. We think it's actually driven by the emission of dust and gas, and some of the dust isn't able to escape gravity and comes back again, splashes down, and you get a cascade effect, and that's what drives these dune structures. We have this nice belly region of the duck, the Imhotep region. We see lots of dusty regions and layering again, and these funny vent-like objects. We also have the Cheops boulder. This was named after the Grand Giza pyramid, because this bunch of boulders here reminded people of the Giza necropolis in Egypt. And for reference, and for the conspiracy theorists, that's what the Giza pyramid actually looks like. So this is about 40 meters, the Cheops boulder. It's used as a kind of 0 point for the axes that we use so the coordinate axes that we use for the comet. So some of those vent hole features, we're trying to work out how they're formed. We think they may be degassing vents that are then gone dead. They fill up with other dust, and then through erosion and subsequent processing, they form these funny circular plateaus. And we see these features on previous observations of previous comets, so at Tempel 1 from Deep Impact, and we also see these large cut-out disc-like, I wouldn't say craters, but depressions, which are similar to what was seen by Stardust on Vil 2. And again, we see this, like the happy region, where this dust laying in the neck region can be compared to Epoxy's observations of Hartley. So the stuff that we're seeing in Rosetta, we've also seen in other missions, and we can study in more depth and then compare that back to the other objects we've observed. There are also these smaller vent-like structures, which seem to be very important in the emission of dust and gas. We think these are formed like sinkholes in Earth, so you have some ice, some volatile subsurface that carves out a cavity, the gas escapes, and over time, the roof of this cavity collapses like a sinkhole on Earth. We think we extend this now and consider the side walls of these cavities having further sublimation driven. So we get this fracturing like we've seen in other parts of the comet, but on the side walls, more sublimation, and then we have the slumping of the side of the cliff. And this we see over time. So there's a cliff edge that you see is starting to slump over time. And this slumping forms, well, we see a talus forming at the bottom of the cliff, and with largish boulders of ice. And we see those, we've observed those as well in these cliff regions on the belly of the duck. And again, at the smaller scales from Shiva on the lander, we were seeing observations of bright patches, which probably could be associated with ice as well. We look at the activity of the comet, tracing back the jets that we see, and we see that they're driven by sunlight. So this yellow line is really where the equator is, where most of the sunlight is hitting. Remember the seasons of the duck. So this is when we're still not in summer yet, in 2014. And then we gradually see, the sunlit portion is going further down, and we get more and more activity being driven. And we see, again, we're showing that sunlight is the major source of activity. That's what's driving activity in these jets. We see that the comet has a bit of a thermal blanket, as it were, and some of this material that I'm presenting will be better presented, much better presented tomorrow in the Rosetta session. This paper basically shows that we see jets continuing to exist after that surface part of the comet has gone into darkness. And we think that's because there's a thermal inertia of the surface layer of the comet. So it's kind of like a jacket that keeps the subsurface warm, but the top surface is already freezing. And it just allows this activity to continue. We can also show this using the MIRO instrument, which can probe subsurface, and we actually shows here that we're seeing temperature enhancements in the neck region. So we've got localized continuation of heat. So there's regions which seem to be warmer than other regions, which may be due to this surface shielding, as it were, this coat. And actually that's shown here, where we see a diurnal frost cycling. So basically what you see here are 3 different rotations, and so here this bright stuff is ice for each of these rotations, but so here you couldn't see it before. So this frost is reappearing every time the comet rotates. It's being emitted from the surface, but then the next time it comes out of darkness, you see this ice again. And this is driven again by the thermal qualities of the blanket of dust on the surface. So as it goes into darkness, the sublimation continues on the subsurface and gets frozen on the surface. So you're replenishing the ice on the surface. And when you come back into sunlight again, you see the ice on the surface. And that's what this cycle is doing. And we're seeing also over time, this is again one of those projections, but this is the belly of the duck, Imhotep. All that this plot is showing you is that the spectral features of the comet were going bluer in the time period up to November in 14, basically indicating that more of the red stuff, the dust, was being emitted, and we were starting to see more blue stuff, which is likely to be more ice-rich. So we're seeing the evolution, the shedding of the coat. We see features that actually evolve in time. You can just about see this, that there are features on the surface that are evolving. And they're evolving faster than pure sublimation would drive. So we have to think about the way the ice is encapsulated within the dust on the comet. Right, this is a tough one. The bottom line here is that we're seeing, it's not a spherical outgassing. This funny shape is driving differences in what we see in the outer atmosphere of the comet, making us think about whether there's heterogeneities, whether there's different parts of the comet that are composed of different things, or whether it's driven just by the way the different dust is being layered over the comet due to the seasonal effects. Or is it telling us something about the way the ice is on the surface of the comet or within the comet, that there are different types of ice that are holding different volatiles in different ways. So all of this is ongoing at the moment, trying to get a feel for what's going on there. We find that the comet is pretty smelly. It's got methane and the alcohol I told you about, hydrogen sulfide, cyanide. So it's a bit like, it's flashing up, but it's a bit like going out tonight to the Funky Monkey. It's that kind of evening, if you know what I mean. The next observations we were making were of comparing the different water that we see on the comet with all of the objects in the solar system. And basically we found that it was very, very different. And that's indicative that this comet is very, very old. It came from the outer parts of the solar system. And this is underpinned by various other observations of different molecules where we see indications that this must have formed in a very cold place. So it's been out on the outskirts of the solar system for a very long time. We can look at the way the comet interacts with the sun, the outer atmosphere of the sun, the plasma of the solar wind. So with the blue stuff is the comet gas, and then the purple stuff is the solar wind being deflected around the comet. You can actually sonify the signal of this interaction. You have the magnetic field in the solar wind being perturbed by this interaction, and you can sonify it, you can increase the frequency of this signature, and you get to hear what it sounds like. See, Mum, I told you plasma was good. You can also see the fact that this gas coming off of the comet stops the solar wind from getting anywhere near the comet. And this is a nice talk tomorrow will be given by Charlotte Goods, who will talk about magnetic cavities, where we actually see this non-penetration of the solar wind and the magnetic field towards the comet. And this was a surprise that we saw it at the distances we were orbiting at. And it really gives us an indication of the dynamics of the object and this interaction. We also look at the dust. This instrument, Cosima, has a plate that's about 1 centimetre square. So this plate on the right is only 1 centimetre. It's a bit like sticking your hand out on a summer's day and catching dust or flies. So we catch these dust particles and we shoot an ion beam at them to see what they're made of. And again, that constrains where we think the comet came from based on what it's made up of. For those of you that come from London, Boris was shot. And he was found to have sodium and magnesium in him. He's probably, the real Boris has got lots more in him. And over time we saw many, many more particles, a lot of dust and different types of dust. Yves Langevin will talk about this in the Rosetta session tomorrow. Actually, the Cosima team name all of their particles to make it easier to discuss amongst the team. So all of these have got individual names, which is a bit unnerving when you know that they're going to shoot people as well. So I know these are named after team members, so these are serious people. And I know Jean-Baptiste was very worried about being shot. We get fluffier dust and more compact grains appearing now with more enhanced activity. We're also seeing compact grains coming more from the more active regions, the more sunlit regions. Again, giving us an idea of how this comet works. What about this fellow? Well, after the deployment, we were out at 20 to then 30 kilometers. We had lots of ideas of where it would be, or the fact is the size of the lander is very similar to the scale size of these features on the surface, so it's difficult to pick out given the resolution that we have available. Maybe these guys stole it. So this was a spacecraft alarm that went off in June. This meant that the lander had come back. And this is what happened. This was on a Saturday night. I was watching Defiance or something on Netflix. And I got this message at 11 o'clock from Armel, the one that had the tattoo on her arm. Sylvain is writing you an official email. Check your mail, we've got it. And of course, I wasn't really paying any attention to the mission. I was watching TV. What have we got? What do you think? It's got 3 legs. So then I kind of clicked, oh, okay, the lander's come back alive. And this was me doing a selfie at night because I was so happy. We basically got the lander back for only a couple of minutes. And this was the issue, that over that period of time last summer, we weren't getting a fixed signal. It was never giving us enough to enable full contact. And ultimately, that's it, folks. Oh. It's a robot. Lots of activity going on last year. So much so that the dust environment was really perturbing our navigation capability, where we need to see the stars, and of course with all this dust we couldn't see the stars. This plot in the bottom shows that as we were going closer to the sun and coming back again, this is the altitude from the comet. So we went out to about 400, 500 kilometers, then we actually did an excursion as well, but we had to get further away from the comet to escape this dust environment, to keep the spacecraft safe. This is actually images from OSIRIS to show this dust environment. So it's like a blizzard, and you're trying to see 9 stars in the background. So that's why it's challenging. We were seeing lots of outbursts in July last year, so coming towards perihelion. These are 20 minutes apart. We saw this massive outburst. In fact, this was associated with one of these diamagnetic cavity observations that I mentioned earlier on. We also saw boulders being flown off or flung off the surface as well around this time. There's another conspiracy theory. Apparently, this looks like, does anyone know Battlestar Galactica? Yeah? Apparently this looks like a Cylon spacecraft. My only question is which series? I think it's clear it's the original series. And we went through perihelion, and it was pretty exciting. We saw these images coming from OSIRIS in August last year, with lots of outbursts and lots of activity going on. There's a big outburst in a minute. Oh, we've already seen it. Is it there? Yeah, there you go. And at the same time, the comet was quite well observable last year and earlier this year from the ground. And we have a great amateur community who are observing for us. They have the opportunity to observe longer because it's up to them where they point their telescopes. And we also have the professional telescopes being pointed in the right direction. This is from September last year, actually, when we carried out that excursion, when we went to about 1,500 kilometers from the comet. The 2 red dots actually indicate the nucleus spacecraft distance. This was an image taken at the furthest point from the comet. This is about 80,000 kilometers in extent at that time, the cut tail and coma. Then I think this is December. Now we're talking about 2 million kilometers. And the most recent image is from March this year. Now you're talking 10 million kilometers in extent, the dust trail. And as Olivier did earlier on when he was showing the size of the magnetosphere of Jupiter, this is basically the scale of the moon in the sky. So this isn't local. This is, if you look in the sky, you'll see the moon. It gives you an idea of the extent of the comet tail as you would look at it. You can't see it, you need a telescope. So we had the extended mission. We were originally going to go to December last year, but we were able to extend. This is us now. There's a comet going away from Earth and the Sun, and in September it will be really far away, and we go behind the Sun with respect to the comet. We'll not have very good contact, so we decided, given all of the constraints we have, that would be the end of the mission. So we've got up until September to do everything we want. These are one of the meetings. This is a meeting from September last year where we were deciding what we would do in the orbits up to that time period. What would the end of the mission be? And people are starting to discuss what they're going to do after Rosetta. And those of you who might have seen Stephen Fusilier give an Alphen Medal lecture earlier this week. He's also a very good juggler. And I know Beth is also forced to eat fire now for his job on Rosetta, and we even have some of the PIs looking for money. And we're still looking at the results. We're trying to work out what the results are saying. This is pure, using a model to work out what your instrument is saying. So these are the plasma guys looking at a scale model of Rosetta to work out what the hell is going on with these measurements, these crazy plasma measurements we're getting. Real model-based science, I think you will agree. And then we're discussing a very recent event. So this is a discussion we had in March based on one of these outburst events that we saw in February 19. So this is all the team standing around just showing plots saying, what do you think this is, and does this match with this observation? And we're talking about this event. You see this massive expulsion of material, which is actually kind of seen first or flagged first by the dust instrumentation on board. They kind of said, well, have you seen stuff on your instrument? And then it seems that as happens, we don't have instruments running all at the same time because of data volume issues. This one, we had many instruments working at the same time, so we've got a very good characterization of this event, which is ongoing and being led by Eberhard Grun. We did a tail excursion. We went out to about 1,500 kilometers into the tail of the comet. I won't go into too much detail for time, but as we were going away from the Sun and behind the comet at maximum phase, so that's the angle between the Sun and the spacecraft and the comet, we took this image, so from behind the comet effectively. You can see that it's backlit by the sun somewhere on the right there. I think this is probably one. I don't like images because I'm a plasma physicist, proper science. But this one actually tickles me a little bit. I like this one. We did a zero-phase flyby, so the opposite. We went across the front of the comet with the sun at our back, and we got these images. This is from 30 kilometers to compare actually to images we took last February when we were at 6 kilometers from the surface, and we actually got the shadow of the spacecraft on the surface at that time. So we do the comparison before and after perihelion, the maximum activity. Then we go through a set of different orbits. Ultimately, we're going to go spiraling closer and closer and closer and closer to the comet, and until we do this at the end of September. Some of you might know a guy called Vangelis, a composer who did music for Chariots of Fire and also Blade Runner, a great film. He composed some music for the Rosetta mission. That was one of the pieces he did. I'm demonstrating basically the interest that this mission has garnered through the activities of the communication. We got a Google Doodle for the new year, in fact. You see the comet, look, there you go, and the lander comes down. Another Google Doodle. We had the astronaut, this is Alexander Gerst on the space station, showing how easy it is to land on a comet by throwing an earplug at one of these robots. We even have, the comet has its own Twitter account as well. He's quite an amusing chap that does that. Monsieur Hollande has named his dog Philet. So interested with the mission was he. An interesting stat here, these is prompted awareness at the bottom. These are people in different countries were asked, or many people were asked, what they knew about Rosetta. Did they know what Rosetta was, what it was about? And this is the percentage correct answer, which is significant, I think, for a science technology activity. Okay, Germany wins every time anyway. But I still think it's good, even though Germany won again. And this is the source of this, I think. This is the team behind the scenes that work on communications here. I just put them all up here. They're the ones that work in the background, doing the tweets, doing the blogs, to keep that machine running. And there's a lot of them involved. In fact, they have published what their thoughts were on this activity. So if you go to this Communicating Astronomy with the public publication, you can see some of their publications. And it's spread far and wide. We have artists really inspired by the mission. Katerina Smirnova came to a meeting recently in March, a Rosetta meeting, and actually showed her artwork, which was stimulated by the Rosetta mission. It's very nice. And also we got some people really interested. There's this guy, some of you may be old enough to recognize him. This is Brian May from a band called Queen. He is actually a PhD astronomer from Imperial College. He's very interested in dust. And he does these stereographic images of everything. And he likes our images. This was that dust jet that I showed you earlier on. So he's even engaged in this. So it's really spread far and wide. I put this up because I have a tenuous link now. Some of you may recognize Colin Pillinger. He was very good at doing outreach. And I think we have reached those heights now with ESA eventually, that we can actually touch many different people. Probably none of you recognize the guy on the right. This is Mitch Harris. He's the guitarist from Napalm Death. I managed to meet Napalm Death recently as well. This is the lead singer. This is actually the head chief editor of Metal Hammer magazine. And there was a boat on the Thames called the HMS Hammer, and Napalm Death were playing on it, and I like Napalm Death, so I got to dance to Napalm Death. But sometimes when you're at a concert, the band will do a tribute to people in the audience. And so this is Napalm Death. This is the impact of, well, this is my excuse for showing this video, really, but it's an indication of the impact of Rosetta, that you even have Napalm Death kind of mentioning science.
Who's like to roll with scientists in the audience? Thank you, good night.
So, for your benefit, that is their shortest song. And just to highlight that everything I've talked about will be much better presented at the sessions, this afternoon and tomorrow. Comets and Asteroids and Dust, and also Rosetta the whole day tomorrow. It's a long day. So where are we now? We're nearly at the end. And so if you want more information, go to these. I forgot I put that in there. They're the websites to go to. So thank you for your extended attention.